Hello everyone, welcome to the next webinar in 12D's training webinar series. My name is Lisa Stewart and I'm the Marketing and Communications Coordinator at 12D Solutions. 12D's training webinars showcase common industry challenges, taking a close look at industry best practices and how these can be implemented using 12D products. The aim of these webinars is to upskill 12D users and broaden their understanding of the capabilities of 12D products. We run these webinars regularly and record them for posting through our website and on YouTube. The previous webinars from this training series, as well as the webinars from our Industry Solutions series, are all available on our YouTube channels if you missed those. While we wait for everyone to finish joining and get comfortable, I'll launch a polling question. You'll have about 30 seconds to answer about which unit of storm frequency you prefer, and then I'll show the results. Okay, so a bit of a mix of answers. I'm glad to see Soggy Carpets per Decade got some votes there because that was certainly my favourite. During this live presentation, you'll be able to type your questions along the way. We'll put some instructions on the screen and we'll answer as many as possible throughout the webinar. At the end, I'll read out some of your questions to the presenter for his insights. Today's webinar will be presented by Owen Thornton, who is both an engineer and a programmer and has been writing, supporting and using engineering design software for 2 decades. He joined 12D Solutions in 2003 as a programmer with an interest in design automation, and he's since grown to become a 12D model specialist in drainage, utilities, volumetrics, plotting and system setup. Owen runs regular 12D model training courses in drainage design, geometric design, customization, and 12DPL macro programming. Today's presentation, Stormwater Drainage Design Fundamentals, Catchments, Rainfall, and Runoff, is episode 4 in this series, which covers the basic and intermediate aspects of the 3 waters modules in 12D Model 14, with special emphasis on the design of stormwater drainage. This session will show the water network editor being used to establish links between water networks, catchment data, and rainfall tables. The statistical relationship between risk and rainfall intensity, frequency, and duration is discussed while producing an IFD table in 12D model format. Various catchment characteristics are then discussed and calculated using 12D model, sufficient to estimate runoff flow rates via the rational method's famously simple formula Q equals CIA. Over to you, Owen.
Thank you, Lisa, and hello everyone. Welcome to episode 4 of this series, but first a little recap. Previously on Stormwater Drainage Design Fundamentals, just a little note here that all of the recordings of the previous episodes of this series, episodes 1 to 3 so far, are available on YouTube, as well as the project, the 12D Model 14 project that's being shown in this series. It's also available for download, and all of this is available on the 12D Model forum. If you follow the links shown here, this is the website to go to for the 12D Model Forum. You do need to log in. You must register and log in to the forum for access. But if you go to the hints and tips, you'll find this particular topic on the forum there, training webinar series, Stormwater Drainage Design Fundamentals, and links to the project and the episodes so far. And as we do more and more of the episodes, there should be 6 in total. I'll keep updating this with links to the new recordings as they get uploaded to YouTube. Okay, so if you do want to have a look at the data, by all means jump on the forum and download it from there, and you may even be able to follow along while I'm talking. Okay, so first up on episode 4, however, this is the first time it's taken us 3 episodes really, and we didn't add any water to our water strings. So this is the first episode in the series, episode 4, where we're actually adding some water. And from a stormwater point of view, the water typically comes from the sky and it's in the form of rainfall. And so we've got a rainfall file in 12D, sometimes known as a hydro file, because the file is not strictly just for rainfall data, it's also for hydrology data as well. But at least for the rational method, it's mainly just about rainfall data. And what we're typically talking about when we create this 12D hydro file, as it's called, or that's the file extension, For each different site location for a job, you'll typically need a special file just for that one site, because rainfall intensities tend to vary across the geography from place to place, and in Australia at least, it typically, they've broken it down into quite a fine grid of, about 1.5 kilometre by 1.5 kilometre grid, I think, from memory. So it's really like, moving from suburb to suburb, you'll need a different file. Now, for the rational method, it's basically about an IFD table, which is intensity, frequency, duration. And this is the basics of the data you need to do stormwater design. So basically, in the famous rational method formula, Q equals CIA, there's an I in there for intensity. In millimeters per hour is how you need to specify it in 12D when you're using metric units. But you do have the option. Some people prefer to think of rainfall as rainfall depths, and in fact, it can be provided in depth. So you've got the option to choose either intensities or depths for your rainfall. I'm a bit of a purist. I prefer intensities because it's an IFD table, and I like I for intensity. But in terms of an IFD table, it's a range of different intensities for different storm frequencies and storm durations. Well, what are frequencies and durations? Well, duration is basically how long the storm lasts, okay? And that's always specified in minutes. And when we're talking about the intensity, it's the average rainfall intensity for that duration. So you could add up the total depth that fell during the storm from a rain gauge, for instance, and divide it by the duration of the storm to give you the intensity, if you like. But as well as that, it also breaks it down by frequency. Now, frequency is, in other words, the probability or the likelihood of the storm event. And it can be expressed in different units as well. In the past, people regularly used a variable called average recurrence interval specified in years, as in like a 1 in 10 year event or a 1 in 100 year event. And people, unfortunately, got to thinking that, say, a 1 in 10 year event means it happens every 10 years. Well, that's a little bit misleading because it's 1 in every 10 years on average. It could happen 5 times in a year and then not happen again for ages. Okay, and so because of that, the powers that be in the stormwater industry, at least in Australia, have started to adopt a new unit called AEP, which is Annual Exceedance Probability. Another set of 3 long words strung together. And it's very easy, unfortunately, to mix these 2 different units up when we support, now that we support both. So do be careful. It's possibly a good thing, but it's also created some confusion along the way. And it is very easy to mix these up because the 2 units, one is almost but not quite the inverse of the other. And so it's very easy, for instance, to mix up, say, a 100-year event with a 1-year event, because a 100-year ARI is equivalent to a 1% AEP. Okay, so there lies the confusion. Once you've got this table, though, of intensities, where on one side of the table is the durations and the other is the frequency, 12D model can use that, and it doesn't need to be a really fine table either. 12D model will interpolate between frequencies and durations where necessary, so you don't need to have every single duration for every single minute and every frequency imaginable listed in the table. 12D will interpolate within it. You do need to specify the correct units, and I'll show you that in just a moment. And also I'll mention that specifically for use in Australia, IFD data may be downloaded from the Bureau of Meteorology website, and that's all that's really needed for rational method analysis, at least as far as rainfall data. If you're doing dynamic analysis, though, you can go to another website called the Australian Rainfall and Runoff Data Hub, where you can download things like temporal patterns and all sorts of other goodies. And in the folder that I've supplied in amongst the projects that I mentioned on the 12D forum in the last slide, I've got some example data too, which I'm going to show you now too. So let's have a look in 12D and see what this looks like on how we can create a rainfall file. I'll jump into the 12D project now. And here's pretty much where we left the project at the end of episode 3. What I have done though is I've added in another network. This is network B. Previously we worked on network A, and I did show a transverse network with a series of culverts and channels up here as well. But I've now got this fairly large network B, and that pretty much completes this design. So we're going to look at the catchments that are going to be necessary for this and the rainfall that's going to be falling on these catchments. So let's start off with the rainfall file. And from your water toolbar up here, it's pretty obvious actually. It's one of the most obvious icons in 12D. The rain cloud there is your rainfall file editor. And this is what it looks like. To create one from scratch, you could just come to the intensity methods IFD table and paste a table that you prepared earlier. Well, I do have one I prepared earlier, and mine's sitting in my customer library, and it is for Brisbane. I'm going to imagine this job is in downtown Brisbane, which is probably not very realistic, but that will be good enough for demonstration purposes. Now, here I've got the country, the state, the city, the date that the rainfall file was generated. So this is the second half of last year when I generated this rainfall data from, or downloaded it from the Bureau of Meteorology, and I've specified the units in that file. And it's a good idea to be so specific here because it is so easy to mix up your units as well. So I've started to adopt this sort of convention with the date that I downloaded the data and what units the intensities or the frequencies, I should say, are in. So I'll select that file from my customer library and hit the read button. And pretty much all I'm interested in this editor, there's a lot of things here down the bottom here that I don't need to worry about for the rational method at least. They're all things that are used by the dynamic drainage and potentially sewer and water supply design as well, but not so much for stormwater with the rational method. The rational method, it's pretty much this IFD table. And if you're not sure what units you've got in the table there, it's a good idea to just have a look on this global data branch here, and it tells you you're using metric units. Your rainfall units are specified as intensities in millimeters per hour here. Now they can easily, if you've got them as depths, then you'd need to change that to millimeters, obviously. And likewise, if your frequencies are in ARI and not AEP, you'd need to set that accordingly. It is very important, though, that the units you specify on this global data branch match the units of the data in your table here. And what the table is, the first column here is your duration. So these are all the durations in minutes, and here are all the frequencies in percent. Now, these are not the straight out standard frequencies in AEP that are now provided by the BOM. It's a little bit more to it than that because I've got these odd ones out, this 39.3 and the 18.1 in the third and fifth column here. But all the other ones, they're considered the standard IFD data. But at least in Queensland, which is a lot of times in Queensland, they follow the QUDM, Queensland Urban Drainage Manual Guidelines. That manual still specifies, whilst they do recommend AEPs, they recommend oftentimes this 39.3%, or you could call it 40% frequency, which happens to be the old 1 in 2 year ARI. And the BOM doesn't provide that easily anymore, and you actually need to download 2 different data sets from the BOM. And I've got a little example here, and it's in the data provided with the project, so you can have a look as well. But if I were to just open up my customer folder, which just from this icon here on the Explore toolbar, that takes me to my OneCust folder, and inside there I've got another folder called AR Data Hub, AR&R Data Hub. And I've got for a range of different locations here, but I'll go into the Brisbane folder here. And what I've downloaded effectively from the BOM are 2 different CSV files. These ones I've highlighted here. They're intensities for a particular latitude and longitude, which happens to be downtown Brisbane. There's the date that I downloaded the file. And I've 2 different data sets. One is called IFDs and one is called very frequent rainfalls. And from this information, I've created this little spreadsheet, which I've called a wizard, but it's not really that fancy. If you open up that spreadsheet, here's what it looks like. And this is just an example. You could find, if you find it useful, that's great. But effectively, it's got 3 little worksheets on this spreadsheet. And these 2 ones that start with BOM AEP and BOM EY, this is just the 2 CSV files that I downloaded from the BOM for this location, and I simply pasted them into these worksheets, okay? And I've colored the various parts green that I'm interested in, okay? So I'm particularly interested in the 0.5 and 0.2 exceedances per year data. And from the IFD data, which is in AEP, I'm interested in all of the frequencies there. Interestingly, though, they also, the BOM now publishes durations for 1, 2, 3, and 4 minutes. And I generally recommend that you don't include those, especially for the rational method, but it has no impact on any of the other methods either. So whilst this data might be interesting in some sense, it's not actually useful for the rational method. You shouldn't really go below a duration of 5 minutes or a TC of 5 minutes in the rational method. So this little wizard sort of has the ability to merge 2 different data sets and filter out the data that you want as well. Because on the main tab here, all we're trying to do here is produce a table like this one that can be simply cut and pasted directly into your 12D hydro file, okay? And basically, all of the cells in this table have been taken from the other 2 tabs, just picking off the data that we need. It also has one little extra feature here is if you ever need to increase your intensities by a certain amount, sometimes you need to do that to consider the effects of climate change into the future. You can multiply them by a particular factor here, and this version of the table is just multiplied by this factor by all these numbers. So whichever table you need, you can simply cut and paste that. So I could just highlight this entire table, for instance, and go back to 12D and come in here, and I could say, oh, let's just delete all of that and simply paste. Ooh, I probably need to, one little trick here, probably need to create enough cells here to do this. Forgot about that. So just hold down the Enter key until you get bored. Try that paste again, and there's our table. Didn't quite paste enough by the looks of it. Just hold it down a little bit longer. Paste, and it's gone all the way down to the 10,080 minute duration, okay? So you can just cut and paste straight into this table if you want. And then, yes, remember to hit the right button after you make whatever changes you want. So now we've got you can have up to 9 frequencies in your table, but this includes not just the standard ones, but also this weird 39.31 and this 18.1% frequency, which is the old 1 in 2 year and 1 in 5 year ARI, if that's what you're more familiar with. And some places are still specifying these that you should design to those particular frequencies or risk factors, if you like, or probabilities when you do your design. So that's a little bit about the rainfall file. There's not much more to it than that for the rational method, and I'm not going to go into the details of all the rest. So I don't need to save this in this case, so I'll just say yes. So once you've got the rainfall file set up for your location, for your particular site, the next task is, well, how do you assign this rainfall file to the water model? And that's pretty easy. Basically, you do it all through the water network editor. The most important thing, though, if you haven't already, you've got to set the method box at the bottom of the water network editor to either rational or any other mode other than none. Now, in our case, it already will be, but it's only then that the hydro file box actually appears on the network editor. So it's just a little point to be aware of there. So back into 12D. If I load up my network editor and I pick on my water model, remember it's the water model named Stormwater that we created in the previous episodes. I simply want to go to the global main tab because my method box down the bottom here is already set to rational. And that gives me sets up all the tabs and sets up the network editor for use with the rational method. And I simply want to come into my hydro file box here on the global main tab in this hydraulic data section, and go to my customer library and select the file that we were just looking at there. Okay, and then hit apply for good measure. Okay, that's all you really need to do to link your rainfall data, your IFD table, to your water model. So that's that step out of the way. So we've got the rainfall now, but before we start looking at catchments, I wanted to show you another little thing here that's useful for stormwater, but potentially some of the other water modules as well, where the rain's not necessarily coming from the sky. And this is the option we have with using direct flow rates, and we can specify direct flow rates in QMEX directly to the nodes and the links separately, and they can be different values for minor and major events if you need them. And the direct flows are a little bit different from doing catchment flows. You're basically saying you're going to work out all the flow rates yourself, and you specify them and they remain constant. They flow constant to the network outlet. They do not reduce or attenuate over time as normal flow rates would due to storage effects. But they are up your sleeve and they are handy in certain situations. Okay, the difference between the two is that the QDG, or grate flow, enters the node directly at grate level, and it's subject to any inlet capacity constraints you might have at that node, whereas QDP, or direct pipe flow, enters the pipe directly. It just magically appears as a flow rate and flows all the way to the outlet as a constant flow rate. So they're typically handy in situations where you might otherwise require extra catchments or nodes and links to be modeled. So say if you had an existing stormwater network, for instance, that was flowing into your proposed system that you're designing, well, you don't necessarily want to have to model that entire existing system into your model. You can just inject a particular flow rate at a particular point, and that will serve a similar purpose. Now, technically doing things like this, it is a departure from the rational method because the flows do not attenuate over time. So it's not quite the rational method, and it's certainly not the dynamic method because these are constant flow rates. But the good news is it's generally conservative because the flow rates don't attenuate. You're going to be over predicting flow rates, if anything. Okay, so I'll just mention this and do a quick demonstration of why I would use it in a particular job like this one. In the case of the rear of allotment roof drainage we have in our system. So let's have a look at that now. Back to 12D. And if you remember from the previous episodes, these two lines here are our roof drainage or rear of allotment, where we've got these grey polygons on the job here within the lots. These are sort of nominal roof sizes within these 10 lots, and it's only these 10 lots that have been identified on this site that are grading away from the roads they're connected to. In other words, the runoff from these sites is not flowing to the road like it normally does in all the others, it's flowing to the back of the lots. And we've provided a couple of lines here for picking up just the runoff from the roofs. In other words, you can imagine that there are gutters and downpipes on all of these roofs that will be connected through underneath the backyard there directly into these pipes, these orange pipes running along the back of the lots. Okay, now there's no open grate or open inlet in the backyard there, so it's not going to pick up the flow outside or off the roof, just if flowing in the garden. It's only going to be picking up the down pipes from the roof. So it's only for roof flow only. And there's a little bit of a complication. According to the QUDM guidelines, at least, you only consider the flows from the roof in the minor event, because the gutters in the major event are considered to be overflowing, and this whole rear of allotment drainage system is considered to be inundated and overflowing and not actually conveying any flow. So there's a little bit of a complication here that makes me think that the best solution is to use direct flows. Now, while I'm here though, I'm just going to take us to the Global Notes tab. because here's a big white canvas basically where you can write whatever you need. And what I've done in this particular model is I've documented the particular design requirements of all the different components of my water model here. And in the rear of allotment drainage here, which is all of the strings named AR something, and there's AR1, which I'm profiling here, the design requirement here is to design or size the pipes in this system for a 20-year ARI. And I've assumed then in each of these 10 lots that I've got a particular size roof. I don't exactly know what they're going to build, so it is an assumption, but I've documented it there. I'm assuming that each one of these roofs just happens to be 255 square meters per roof. Okay, but in the major event, we assume the whole system is ineffective. And so all of the runoff from these roofs is going to get into this system in the minor event, but in the major event, it won't get into this system. It's going to run dry effectively, and the runoff from the roof will actually spill off across the other properties and eventually down to the road network, and will be picked up by road pits. So that's the complication that makes it harder to do with catchment polygons and makes it easier to do with direct flows. And so what I've got here is a little sort of manual rational method calculation. You can see the Q equals CIA formula pretty much, slightly more complicated. Without going into any detail there, for my Q20 or my 20-year event, I'm looking at a flow rate of 16 liters per second per roof, or 0.016 QMEX per roof. And I'm going to allocate that as QDP, or direct pipe flow, to these pipes. Okay, and I'll just quickly go through this and show you how I would go about doing this. First up, I'd probably want to, because I'm doing something a bit unusual, I'll probably make a note as to how many roofs are going to be connected directly to each one of these pipes in this part of the system. It shouldn't take very long, but I'm going to make use of the link notes tab here, because as well as a general notes tab on the global tab, each node and each link has a notes tab as well, where you can make general notes. And I'm just going to say, well, this first link in the system here is going to have two roofs connected to it. So I'm just going to put in a little note here, roof for the minor event, and I'll just copy that to the next one. So go to the next pipe and paste. This one's actually going to have 1, 2, 3, 4 roofs connected to this pipe from the downpipes. Now, we're not bothering to model any of the downpipes, so we're doing a little bit of conceptual stuff here. We're just trying to get the runoff from these grey areas into the pipe. So that will do that one. Go to the next one. The next one will have, I'll consider both of these roofs connected to this reach, so another 2 roof. This next pipe, I'll probably skip over. This one won't have anything connected to it. It's just there to turn the corner around the way the lot boundaries are there. So I'll skip that one. This one will have just this roof here. So that'll be 1 roof. And likewise for the very last pipe, 1 roof. Now you might think, why have I bothered to do all of that? It's just notes in the network editor. You're not going to see that. Well, actually, you probably are going to see that, because if I hit the plot button, those notes appear because I've chosen to, through my drainage plan PPF there, I've chosen to plot that attribute, which is just a pipe attribute called remarks. And I see the notes that I've made there, and it makes it easier for me to keep track of what I'm actually modeling while I'm doing this. Okay, so that's why I've gone and done that. The next step then is go back to the top of my AR1 line there, and I'm going to go to the link main tab, and I'll quickly go through and set all the flow rates. So with 2 roofs, that is, I'll come into the QDP minor box here on the explicit link main tab, and I'm going to type in 0.016 for 16 liters per second. This is specified in QMEX, this flow rate, and I've got 2 of them, so times 2. I could have done that in my head, 0.032, and move to the next pipe. This is just for the minor event. Remember, it'll be 0 for the major event. This one's going to have 4, so 0.016 times 4, 64 liters per second. This one is 2, so that's 0.032 again. This one has nothing. This one has 1, so just 0.016. And the very last pipe over on the other side, 0.016. So that's just a quick way we can get some flow into the system. Now, I haven't specified it as QDG because it's not entering in through these inspection pits. These are sealed nodes in the system here. They're going to be, the downpipes are going to be tapped into these PVC pipes that are running along the back of the node. So that's why I'm going with QDP. When we come to do the major event though, all of the flow rates being generated for these roofs are going to need to be allocated to these various road pits down here and here and here instead, and they will be specified as direct node flows, or QDG, which you'll find on the explicit node hydraulics tab there, and you can specify the QDG major once we get to the major event. I'm not going to bother with that now, but now that I've got this, just without even having any catchments yet, I've just assigned a few flow rates directly. I could go straight to the analysis and I can see there's my hydro file that I set up, but I'm not even using the hydro file yet. This is going to just do a quick sizing of just these pipe systems and possibly all the way to the outlet here as well. And we'll just see what sizes we come up with. So there's my AR1 line. At the moment, they're all set to 150 millimeter pipe. Now, if that's our minimum pipe size, and we want to check this, let's just have a look in our preferred pipes file here. This is on the analysis panel, and I'm just looking at the main tab here. In the next episode, we'll look at the flood extents and all the things you can do there. I might just tick that one off for now. And I'm not really interested in bypass flow yet because I don't have an overland flow model set. This is just a preliminary sizing for this roof drainage system. And it's also going to allocate a hydraulic grade line along my section view profile as well. Okay, so looking at the minimum pipe sizes here, or the preferred pipes file, if I open that up, this is going to choose from a range of different pipe sizes here, all of the circular pipes that we see here, skipping over certain ones. I certainly don't think I'll need any of these larger ones for this roof drainage system, but the PVC pipes can get small. Now, some people might say, oh, don't use the 150, they're too small. That's fair enough. But they typically get built up to like a 375, I think, or even a 450, the largest PVC pipes. I'm going to just leave on the 150 just to see if it does anything. In fact, I'm not changing this one at all. And without going into too much of the detail here, it's just going to do allocate those direct pipe flows, and they will all accumulate to the outlet there. So the flow rates in these pipes will get bigger and bigger and bigger. And it will flow all the way to the outlet and into the basin here through this line. So it's going to continue all the way on. Even though there's no catchments assigned anywhere, those direct flow rates will already work. Now my plots are already set up. I've set up some reports. We'll have a look at those later. For now, I just want to hit the run button. And lo and behold, it has gone and sized my system and set this cyan hydraulic grade line there. And lo and behold, we've got water into our system for the first time, at least for part of the system. And we can see the pipe sizes have changed too. They've gone up to 375s in some spot, even though it's starting at a 225 at the top here. And this one is that one looks like a 150 diameter pipe there. The pipes have gradually gotten bigger. And we haven't needed anything bigger than a 375 to get us all the way to the outlet. But you can see on our trunk line, line A0, we set our tailwater level there in the previous episode. And it's backing up all the way up to this node here, which is beyond that though. When we look further up this line, the hydraulic grade line is just dead flat because there's no flow in that system. And in fact, the whole system is just backing up because in theory, the water could back up the line there from the roof drainage if there was no other flow coming into the system. Okay, so there's a quick, I guess, demonstration of direct flows. But we do want to talk about catchment areas. It is a big part of this webinar today. And when we talk about catchment areas, they don't have to be done from polygons, but they normally are. They can be specified either directly in hectares, or you can calculate them from polygons. Get 12D to calculate the area by drawing polygons. Each inlet node in your water model can have up to 5 different catchment areas assigned to it. You don't have to use all 5, you can use just one or as many as you like to use. But within each catchment area, and up to 5 per node, each individual catchment area can be then further subdivided into impervious and pervious, or otherwise known as paved and vegetated fractions by the percent impervious value. Okay, so it effectively takes whatever area you've assigned and breaks it up based on whatever percentage it is. So if it's 30% impervious, then 30% of the area will be considered paved and 70% of the area will be considered vegetated. And each one of those fractions can be set with its own independent hydrological properties, and they can be set either explicitly on that fraction or by default on the defaults tab of the network editor. Okay, and what we're talking about with these hydrological properties, well, it depends on what kind of hydrology you're doing, but for the rational method, it's basically just the time of concentration, TC, and the runoff coefficient, or the C value of each fraction. And again, they can be specified directly by just typing in values, or you can calculate them via various means, various formulas to match whatever guidelines you happen to be following. Okay. There are a couple of other variables here, length, slope, and retardance. These can be specified if you're wanting to calculate a TC rather than just type one in. There's various formulas that will use these length and slope and retardance values of each catchment, depending on what TC method you use or specify. And in order to calculate the length and slope of a catchment, well, we can use 12D to do that as well. You can draw things as, and I'll show this a bit later, TC strings can be drawn within your catchments, and 12D will automatically use those to assign levels to them and calculate the length and determine the equal area slope of your catchment, which is typically the slope that's used for doing catchment analysis. And it will measure that from the finished surface tin. Okay, now the important note to note here is so far we've got an intensity from the rainfall file, and we've got an area coming from the catchment area, and we have a C. There's your CIA in the rational method. But how do we relate the I of the rainfall intensity to this? Because you don't specify an intensity for a catchment. What you do is you specify a time of concentration. That is the time the time it takes for the whole catchment area to contribute to the bottom of the catchment at its discharge point. Okay, and that is a critical factor, and it's also a very rubbery factor too. You know, our general recommendation from me would be to treat all times of concentration and all C values with suspicion at all times, and to do sensitivity analyses on them, because don't expect any high level of precision in any of these numbers. Okay, it is not a precise science, stormwater design, if it's even a science at all. It could be part art as well. But the rainfall intensities are derived from the IFD table simply by considering storm durations equal to the length of the TC of the catchment. Okay, now it's very simple if you've just got a single catchment fraction. It's just straight out Q equals CIA. It gets a little bit more complicated than that once you start adding multiple catchments, but not much more complicated than that. And I won't bother going into the details there. If anyone's interested in the details, I have written up stuff in the past and I can dig that up and send you an email or something. Okay, so that's what we're talking about there. Well, I have a look at that in 12D. Let's just sort of jump onto the top of my line A0 here and just go to the catchment tab here, the explicit catchment tab. Now, you'll see here set number 1, 2, 3, 4, 5. These are the 5 catchment areas you can assign per node, okay? And you can do it on an explicit or a default basis as well. If I go to the defaults tab, this is data that applies to all nodes. Ignore what it says there. It's not, shouldn't be there, that comment. But under defaults catchment, you can see the same set 1. You can set all of your defaults for your catchments here as well. And I'll come back and talk about that in a sec. I'll come back to the explicit tab though. if you don't have a polygon, you could just type in an area. You could say, well, this is actually half a hectare, 0.5. You type it in hectares. As soon as you press enter, the tab comes to life. And you can say, well, what percent impervious is it? Well, let's imagine that the catchment assigned to this node was entirely paved. I would say it's 100% impervious. If I hit enter, it blanks out the pervious because it's only the impervious fraction that's in use. Likewise, if I change it and say it's actually 0% impervious or entirely vegetated and hit enter, it blanks out the left-hand side and gives me the right-hand side. If I type in some number between 0 and 100, like 50%, and hit enter, it enables both sides, both fractions, and whatever area you've typed in there, well, 50% of it will be impervious and 50% will be pervious. That's how it works, okay? So yeah, if you've got direct areas, you can go to town and type them in, but we can take it a little bit further than that because most people will use catchment polygons. I'll go through the details of all of these individual characteristics like TC method and length slope retardance and the TC and the C values. I'll do that by example in just a sec because that's just a very brief introduction to the catchment characteristics. What we're really kind of, the thing that takes most of the time in all of this is the catchment polygons and potentially the TC strings. The TC strings are a little bit quicker and you don't need to use them quite as often. But in order to allocate your polygons as catchment areas, you use the Set Catchments button. And I won't just read this out. I'll just sort of show this up here for a moment and say, look, we're going to go through the Set Catchments button in the network editor now, which is going to do all the assigning. And we're going to talk about where the polygons need to be in your model, in your project, sorry, and what models they need to be in, what rules there are, and what tips I can give you for how your polygons and TC strings are constructed, and how it all fits into this thing called the catchment file, and how we can label our catchments as well. Okay, so I'll do this more as a live demo than just reading out everything in detail here. Let's go back to 12D here and let's imagine that we have gone and drawn a whole bunch of polygons for this stormwater model. I might just make the view a little bit bigger. Now, I'm not going to sit here and pretend that it's an easy task to just sit down and draw a whole bunch of catchment polygons for a water model. It isn't. You can expect to take a fair amount of time to do it. And later on in the webinar, I'll give you a few little tips and tricks, but in truth, there's nothing fantastic at this stage in 12D that's going to automate this process. It is possibly the most time-consuming part of stormwater design. But let me imagine, I'm not going to spend too much time telling you how to draw polygons, but let's just have a look at some data that we may already have. So I've got a couple of models here. One's called Stormwater Catch 1 Roads. Now these are just these polygons in gray, they've got a little bit of translucent fill applied to them. And these are just polygons that I've drawn appropriate for all my inlet nodes, just covering the road reserve. And I've put them all in one particular model called SW Catch 1 Roads. I might just take those roof polygons off the view for a moment. So it's just in this one model called Stormwater Catch 1 Roads. Okay, now I might have, that's not the whole story though, because all of these lots are running onto the roads as well, and they're going to go into the inlets as well. So I do have another model of polygons here, Stormwater Catch 2 Lots, like so. And you can see these polygons have got a couple of interesting features in them. As well as being in a separate model, some of them have these little black holes in them. Now this is just a simple feature within 12D. There's a toolbar called CAD Hole, and you've got options to add or remove holes from polygons. Now a hole in a polygon is it's basically like a child string within a parent string. So if I were to just as a simple example for say this polygon here, now this polygon, includes 3 holes. In other words, the area of these holes subtracts from the total area of the parent polygon. Okay, now anytime you need to consider polygons with holes, it's a great little option to have up your sleeve. So if I were to just remove these momentarily, I can pick on the polygon I want to remove them from there, and suddenly they come back as actual strings that I can, or separated from the parent polygon, and they've all got their own area, basically. If I wanted to re-establish them as holes, I'll come back to the hole add, and I'll pick on the parent string, that one, and I simply select each of my 3 child strings, and I get my holes back. Okay, and that's just a bread and butter piece of the CAD functionality in 12D. Anytime you need to do something like this, and you can see why I've done it. These are where my roofs are in my rear of allotment, and I don't want the area to be sort of counted twice when I run these catchments off to my road pits until I get to the major event, okay? So what do I do with all this catchment data though? Well, if you want to get everything, you can draw these polygons any old how, really. I don't care if you draw them clockwise or anti-clockwise. I don't care if you use a particular line style. I don't care whether you put solid fill on them or not. I'm a solid fill kind of person. I like this translucent fill, sorry, and I don't like putting any fancy line styles on them, but that's just my preference, and it's just a preference. The one thing that I'll say, rule number 1, when you're drawing your polygons, if you want it to be as pain-free as possible, when you start drawing your polygon, be careful where you place the first vertex of your polygon, okay? The first vertex of your polygon should be closer to the node you want to link it to than any other inlet node, okay? Because that's how the Set Catchments button goes, and it automatically assigns catchments. Okay? It's based on where the vertex 1, or the first vertex of the polygon, is in relation to the inlet nodes, okay? Now, if you get it wrong, or you've already got a set of catchments drawn, it's not the end of the world. You can go and manually assign them. But the first thing to know, once you know that rule, I guess, or the second thing to know is once you know, once you've got some polygons, you've got to know where to put them. You've got to put them in specific models, and those models need to be specified in your catchments file, okay? And that is on the Global Utility Models tab, okay? In the last episode, we set up the road design file and the service clash file. Well, here's where we set up the catchments file. You can just type in a name and create one, but I've got one already made in my customer library called sw.catchments. And I can click on the folder icon and open it up. And here is where our 5 different catchment sets can be defined. Now, this particular example is only using 2 of the 5 sets. Each one of these rows is a set or a catchment set. And I'm not using any TC strings in this stormwater model at all. I'll have a look at them in the transverse model a little bit later. You can also assign colors here, whichever colors you like. I've chosen some of the graduated colors that we have available. Now, it's entirely up to you whether you want to use multiple sets or just one set. But because I've broken my polygons up into different land uses versus the roads versus the lots, I find it easier then to set the catchment characteristics that I need to. The downside, of course, is you're drawing more polygons, which is nothing to be sneezed at. That's a definite downside. But it can be as simple as this. The main thing to note is all of the polygons for the roads need to be in this model here, and all of the polygons for the lots need to be in this model here, okay? So the polygons need to be in the right models. Other than that, it's just a matter of hitting the right button to save the file if you make any changes. And from each set, you can have 1 polygon per node. And that's how you get your up to 5 polygons per node allowed. And those polygons, the area will be automatically calculated and will have some data assigned. So with our catchments file in place, all I need to do now is hit the Set Catchments button. And suddenly, all of my catchments change color as long as they get assigned. If anything doesn't get assigned, its boundary will be colored red there. So don't set the error color to match one of the colors of your polygons. You won't be able to spot it. But all of my catchments have been successfully assigned there simply by drawing them in the right spot, being careful with vertex 1, putting them in the right models, defining that catchments file, and hitting the Set Catchments button. Okay. At the same time, it's also labeled them, so I can add on this model called Stormwater Labels Catchment, and it's put in a little label model there telling me the name of the node that it's been associated with and the area in hectares of each polygon. Okay, and you can go through and check that. If it's from set 2, it's got a 2 in brackets after the node name, but you can go through and check that everything's been assigned correctly. Now, I'm drawing my polygons on the top of the view there. I don't know if it makes much difference, but I'm just going to move those polygons to the back, models to back, like so. Makes it a little bit easier to see, and I'll send my tin to the back behind that with this views, send tins, rasters to back. And that's a little bit easier to see. And if I use the network editor again, now that I've got catchments linked in, you can also see, as well as the highlighting of the current node and the current link, it's also highlighting the different catchment polygons. Okay, and I can move on the catchment tab, I can jump from set 1 and set 2 and see the different catchments being highlighted there as I move around. And if I move off the catchment tab to, say, the node tab, it highlights all of the catchments assigned to that node. And you can, again, loop through the network there, looking at the highlighting to check that your catchments have been assigned the way you expected them to be assigned. Okay. All the way along, you can look on the catchment tab, though, and you won't see catchments on an outlet or at manholes, but say for our inlet nodes, our sag pits and on-grade pits, you can see the areas have been assigned there. You can see the name of the polygon, and you can go through and check everything that you need to check there. Okay, so here you can see that this node has both a set 1 polygon and a set 2 polygon and so forth. Now, again, if you ever find a case where the wrong polygon gets assigned to the wrong node, you can come and use the pick arrow here and go and pick it for the appropriate node and get everything manually assigned that way. And that's something you might have to do at times if you haven't been careful with where you place the first vertex on the polygon. Okay, so that's in a nutshell how you do assign catchments. The only thing I'm missing there is TC strings, and I can probably show that easily enough if I just take all of that off the view for a moment, and we'll do a similar process here for the transverse model. So SWT. Here, though, I've got 3 models of catchments already drawn up, plus another model called TCP3 for the stormwater transverse model. Now, this is the culverts and channels that we looked at very briefly in the last episode, and I've got an almost identical sort of data structure here. This time, though, I'm not going to be editing the stormwater model. I'm going to use the pick edit and go and edit my transverse model, the SWT, T for transverse. And on the global utility models tab, again, I'm going to pick a catchments file, but this time I'm going to pick a slightly different catchments file. It's the SWT catchments. If I have a look at that, it's slightly different from the other catchments file. This one's using 3 sets first up, and it's also in the 3rd set, which is for anything that's not a road or not a lot. There's this native vegetation up in the hills here to the north. And it's also got this extra model specified, which are the TC strings. Now, you generally only draw TC strings for the larger catchments, and typically only for the pervious portion or fraction of the catchment. The impervious TC of a catchment is typically going to be 5 minutes. It's very rarely longer than 5 minutes, so you don't really need a TC string, because all a TC string is going to do is help you calculate the time of concentration. And it's generally only for the pervious or vegetated portion of the catchment that you need to do that. Now, if you've never seen these arrowed line style before, this is actually the good old flow line style, but what you'll notice when version 14C2H finally gets released, this is a pre-release version that I'm running today, you will see a new line style in there for that flow line if you're used to using that flow line style. And this is now what it looks like. It's a little bit easier to see on screen. But the rules for catchments in the transverse model are identical. You still be careful of where you put vertex 1. For TC strings, however, a TC string doesn't have to have any levels, but you draw it from the top of the catchment, drawing to the bottom to its discharge point, trying to sort of estimate the longest time path for the catchment to concentrate or flow and contribute fully to the discharge point. There is a requirement for these TC strings though. It is the last vertex, the end vertex on the TC strings must be closer to the node you want to link it to than any other inlet node, okay? So that is an important thing to note. And you can't sort of manually reassign these ones, okay? They're just, they're not used nearly as much as the catchment polygons, but they're up your sleeve if you like them. And yeah, I generally just use them for the larger catchments because I'm not a stormwater savant and I can't just look at a polygon like that and say, oh, that's a 15-minute TC or that's a 10-minute TC or whatever, okay? I do sometimes need a bit of help, and that's what these TC strings can do. Okay, so again, once you've set all of the data in the right models and you've set up a catchments file, you specify the catchments file on the utility models tab, and then again, you hit the set catchments button. Okay, again, I've used different colors for this one. Again, we get labels as well. I've used different colors for that. SWT labels, there we go. And if I were to have a look at this one, now I just happen to be on this largest catchment in this whole project. If I go to the catchment set number 3, because I've used set number 3 for these vegetated areas up in the hills here, I can see a whopping great 8.8 hectares as it's calculated. And if I zoom in on the label there, it's 8.8 hectares is exactly what I see. And it's been allocated to node T11 from set number 3, which is what I'm seeing here. T11, set number 3, 8.8 hectares. As well as that though, it is also allocated this TC string to the set number 3 pervious fraction. And it's gone and measured the length of this TC string. And it is also graded this and calculated the equal area slope relative to the finished surface tin and calculated the length and slope there and put them in the box for you. So that if you do choose to use a particular TC method that uses those lengths and slopes, such as the Bransby-Williams equation, which I think is the default TC method for this particular fraction, it's already got some reasonable, decent numbers to plug in, and you don't have to sort of do them yourself. Now, just to show you what these TC strings look like once they get assigned, I could repurpose my cross-section view here just by profiling that one, and you can see it's just set this yellow TC string on a constant grade, okay? That's the software did that. They originally didn't have any Z values at all. The software has done this, and you can see this is what the equal area slope is relative to the red slope there, which is our finished surface tin. The area below the yellow line is equal to the area above the yellow line. That is what the equal area slope is. And it's favored by hydrologists for doing this sort of thing because it always tends to be weighted towards the predominant slope of the downstream end of your flow path. And that's where most of the flow happens to be. Okay, you certainly, if this is the average slope, it would go from all the way up there, all the way down to there, and that would be much, much steeper. But because this is a catchment that's very steep at the top and then flattens off, the equal area slope is a bit flatter than that, which is supposedly gives a better prediction using all these various weird and wonderful time of concentration formulas. Okay, so that's a little bit about TC strings. I am hitting my time limit now. So I'm just looking at anything I might have missed along the way. I think I've covered everything I wanted to. The last little slide then, and I know I sort of glossed over the whole how do you draw polygons inside 12D. Again, there's lots of different ways to draw polygons, but there's nothing fantastic in 12D at this stage, at least, for actually drawing catchment polygons. Lots of great tools for drawing polygons, but if you need to sit down and create a whole lot of catchment polygons, my tip would be first up to allocate more time than you think you'll need, because there's no getting away from the fact that at the moment it is a very time-consuming process, and it is possibly the biggest bottleneck in the whole stormwater design process. My general tips though would be to use the tin contours as a guide and adjust the tin contours via the view settings to suit your particular job. Use the CAD polygon toolbar. The freehand and boundary tools are very good within that for drawing polygons, and populate your CAD control bar using the eyedropper, the same as eyedropper. If you don't know what that means, I can show you, but I am running over again. One little tip that I always do that I see a lot of people don't always do this, when you're drawing lots of polygons next to each other, consider snapping the vertices of each polygon onto the vertices of adjacent polygons. Now, the reason you want to do this is, generally speaking, those polygons may need to be moved at any time in the future. If you start moving nodes around and changing designs, those polygons are going to need to be moved. And if you snap the vertices of your polygons onto each other, it means that you can move adjacent catchment boundaries together with the boundary you're actually moving using the move point and move points icon. I'll try and do a little demo of this before we wrap up. I've already shown the CAD hole toolbar for adding and removing holes whenever you need it, very, very handy. There are a couple of tools here, very useful tool, this split catchment tool under the Stormwater Tools menu. It's relatively new if you haven't seen it before. It was always quite a painful job actually if you had a polygon that needed to be split in two because you needed to add a new node somewhere or something like that. And another option there is the raindrop option, which is favored by some users. I can't say I'm one of them, but some people do use it. Other people use downhill strings even to help them along the difficult process of creating catchment polygon models. There is a little teaser in grey here about version 15. I'm not allowed to say any more than that, so I won't. But let me just do a quick little demo of some of the points here. Now that I've got these catchments assigned though, I might just do a quick analysis. I'll go back to my stormwater model, in fact. Just take off a few of these details here and add back on my stormwater stuff. That one and that one. Like so. I think that'll be. So this is where we were before. I already had run an initial analysis just to do the direct flows in this roof drainage, but now we've got all this extra catchment area. We have added a whole bunch of potential new water into our system. So why don't we just jump back into the stormwater network momentarily. Probably doesn't hurt to, after signing catchments, to run set node details and regrade pipes. Wasn't that what I said last time? Is if in doubt, press the button. And let's go straight to analysis now. And let's see what changes. If I zoom right in to my outlet pipes here, and I profile line A0, which is my outlet line here, running down the road here. Let's see if the pipe sizes change. Let's see if the hydraulic grade line changes with all these new catchments. I'm still not considering bypass flows, so there's a big assumption here that I'm just assuming that all of these catchment flows are captured by their nodes entirely. And I'm not at all testing whether any of my nodes are actually in the right spot in terms of controlling flooded widths. That's another problem entirely, which is what the flood extents tab is all about, and that's what I'll be covering in episode 5. For now though, let's just do a quick preliminary analysis and a quick pipe sizing assuming all of these catchment flows are captured by the pits. A lot of the time in a minor event especially, that's not an entirely bad assumption to just assume that there's no bypass flow. So let's just go ahead and hit the run button there and have a look at the hydraulic grade line change and the pipe sizes change. You can see that's made a big difference. And we've got now 675 diameter pipes there with much bigger flow rates. And we've got pipe sizes extending all the way up the network there. We've got 450s, 375s before. And so we've got water through our whole longitudinal system now there too. But what I wanted to show just quickly with the catchments, couple of little tips there. What I mean with the CAD toolbar, this is the CAD polygon toolbar, and it's specifically this freehand and boundary polygon options that I use a lot. And you can just, for instance, say you wanted to draw another polygon from this set number 2. Use this eyedropper same as icon to populate this CAD control bar at the top. Eyedropper, click on that polygon there, and that's populated the model name and the color and all of that. So you can just begin drawing polygons in that same model. If, let's say, we wanted to draw another set number 2 polygon, say for this node here, not that it is flowing to this one, but I could say, use my polygon freehand and say I'll start it pretty much near or close to the node. That's my first vertex, and I'm going to snap onto the vertex of the adjacent polygon. Okay, probably easier if I take off the labels actually, like so. And let's just imagine that this is what the catchment looks like. I don't know if it does. It might be worthwhile toggling on the vertices of your catchments. That would help too. So you can see the little cyan crosses where the vertices are, helps you know where to snap. And this is the process, is what I'm talking about with the CAD tools inside 12D. Now that's not actually the right catchment for this node here, but I'm just going to imagine it is. And if I just jump back into the network editor, having drawn that polygon and hit set catchments, suddenly it gets applied with solid fill. And on set number 2, I can see it's appeared, and we should get a label in there too. I shouldn't have turned those labels off. Labels catchment. Yeah, there's the label there for this CO1 line, 0.1457. There we go. Okay, so there's a quick example of drawing polygons and snapping the vertices as well, which is another point I made. Already covered CAD holes. The split catchment and the raindrop option there under Stormwater Tools. There's raindrop here, otherwise known as the teardrop macro, and split catchment, which is this one here. Now, I won't do a demo of this. They're pretty straightforward to use. If you do have any particular issues in using them, let us know on the forum by posting something up there. Again, some people use downhill strings to help them out in this process as well. But hopefully with version 15 coming out, there will be something new in this space. I can't say too much about it because it needs to be developed properly yet. But there will be something that hopefully will make this process a little less painful, especially for road polygons and dealing with when you've already got design strings in place. So I think that's where I'd like to wrap things up today. Thank you for your patience and letting me go over time again. I'll send things back to the PowerPoint for now and open the webinar up to answer any questions that might have been sent in.
Thanks, Owen. Yes, we did get quite a few questions through from today's session, so I've just picked 3 to run through quickly before we finish. Mike in Perth has asked, how do you set a single C value for a catchment rather than 2 for impervious and pervious?
Yeah, there's the best way I think is to set the percent impervious value to 0 and treat it as though it's entirely pervious. So just use the pervious fraction of the catchment. It does happen from time to time, mainly when your design guidelines dictate to say thou shalt use this C value and they don't break it up. That's the case when you do that. So effectively the percent impervious value becomes somewhat irrelevant. And you just set it to 0 and you just use the pervious fraction there, and all your CP values and will become C values effectively. So that's in a nutshell the way I would do that. The methods, I didn't actually cover the methods of calculating C values, and I'll do that when we talk about the analysis in more depth in the subsequent episodes. Yeah, there are various different methods for calculating C values, and they probably won't work if you do that sort of thing. It's mainly intended for when you're setting those C values directly.
Okay, great. Alan in Brisbane asked, with QDG, if you put a flow to a field inlet with a small ponding depth, would the flow be attributed to a bypass string and flow above ground?
Yes, it would.
Great.
Yes, if whatever doesn't get, because it's subject to inlet capacity, anything that doesn't make it into the node will bypass. A sag node will only bypass, of course, once the ponding depth reaches the maximum ponding depth, and there will be a certain inlet capacity at that depth. But if your QDG is greater than that, well, whatever the amount greater is the amount that it will bypass.
Okay, sure. Thank you. And just one more. Sarah in Melbourne said, when would you turn the partial areas tick on and off?
I would say pretty much always have it ticked on. I virtually have it rusted on in mine. Now, if you have it ticked off, you're going to predict, in general, you're going to predict smaller flow rates, sometimes a lot smaller, sometimes not much difference. From a computational point of view, it really makes no difference whether you have it ticked on or off. But from a results point of view, the partial area check is doing a slightly more sophisticated and slightly better estimation of the flow rates, because whilst, when I was talking about the time of concentration, that's for the full area to contribute to your discharge point. Okay, now as TCs get longer or storm durations get longer, rainfall intensities get smaller. So the bigger the catchment is, or the bigger the TC is, the smaller the intensity will be. And therefore the smaller the flow rate will be for the same C value, if you like. What the partial area tick is all about is it's saying, well, it actually looks at smaller times of concentration within that catchment and saying, well, what if a smaller portion of that catchment contributed with a higher intensity? And it's kind of a classic mathematical maximum minimum problem, trying to find the sweet spot that gives you the peak flow. Now, from my personal perspective, unless you're told otherwise, I would always leave that tick box rusted on.
Thanks for that, Owen. And sorry to those attendees whose questions we couldn't get to live, but I'll email you through those questions shortly, Owen. The recording of today's webinar will be available in coming days through the webinars page on our website, as we've mentioned, and on the 12D Model YouTube channel. And yeah, as Owen was saying before, I think we'll probably add this link to the 12D forum as well, in with those others. We'll be emailing out the link to all registrants, and I'll be putting links to the previous episodes in that email too for easy reference. And in the meantime, keep an eye on our emails and social media for details of future webinars. We're going to be booking some more of those in soon. And if you need to contact us in the meantime, our details are on the screen now. That concludes our presentation for today. Thank you all for attending, and we hope to see you at future webinars.